we're going to go ahead and take a look at graphing a fourth degree polynomial function. This would be similar to the problems, I would say, 81 through 98 in section 5.1. And I already have a video where we're graphing a polynomial function that is a third degree. And these are pre-factored. In the next section, in 5.2, they won't be factored, and we'll have to tackle that also. But these are already pre-factored. So the first thing we're going to do is look at the endpoint behavior. Because it's an even degree, you have x to the second times x would be x to the fourth. And it's positive because the value in front here is a positive 1, or at least it's implied to be that. We're going to go ahead and say that a even degreed positive function is going to go ahead and, so it's even also, it's going to go ahead and have both ends either go up or both ends go down as far as the endpoint behavior. It turns out if it's an even degree, and I put negative infinity in here, negative infinity squared is positive times negative infinity again is also positive. So I expect it to go up on the left. Out here at negative infinity it will go up. And here for positive infinity it's going to go up because positive infinity squared times infinity will also be a positive value. So we think for large values, both in the negative and positive direction, it's going to point upwards. And this is kind of similar to a positive quadratic function, which is also an even degree polynomial function. We would see both ends go up. Okay, so let's find the y-intercept. So that means putting 0 in for x. We're going to evaluate f of 0. And when you put 0 in here for x, you're going to really just get left with negative 2 squared, right? 0 minus 2 would be negative 2 squared times 2 times 1. And that product is 8. So 0, 8 is our y-intercept, and that would be our first point, and it would be right here at 8 on the y-axis. Okay, so then because it's already factored, we don't have to worry about finding the x-intercepts. The x-intercepts are going to come out of our factors. In the next section, we're going to actually have to break the function up into factors, and then we'll be using this information right here. But we could go directly and talk about the x-intercepts and put them right here in step 3. Because if you have these factors, and you use the zero product property where you let y be 0, that would be where you would find your x-intercepts. And you set each of these factors to 0, you would go ahead and have zeros at 2, negative 2, and 1. I'm sorry, and negative 1. So we're going to have zeros at 2, negative 2, and negative 1. And the multiplicity, because this is squared and there's 2 factors of 2, we're going to go ahead and call this a multiplicity of 2, and that graph is our graph is going to touch at that point. At negative 2 and negative 1, we had a multiplicity of 1 here, and therefore it's going to cross at those points. So that gives us a little bit of an idea here. Let's plot those points on the x-axis, and we're thinking here at 2, we're expecting it to touch in some way, either like this or like this. We're going to find out more about that in a minute. And then at negative 2, we're expecting it to cross, and at negative 1, we're expecting it to cross. Okay. We also know this about polynomial functions. The maximum turning points is 1 less than the degree of the function. So at most, this is going to have 3 turning points. It may have less than that, but at most, it can only have 1 less than the degree. Okay, then we're going to now just throw this in our calculator. We already know a lot about it. We're expecting it to go up on the left, up on the right. We're expecting it to cross through these two. So maybe something like this, it's going to come down, maybe come back up, and come back down. And then it's going to bounce off of this, right? Because it had a multiplicity of 2. And this is what we're anticipating, but we'll use our calculator now because there's going to be a maximum and minimum point that we're not going to be able to calculate like we could with a quadratic function where we could use a formula to calculate the vertex. So to save a little time, I already put this function in the calculator right here. But I didn't set the window, at least I don't think I did, for this to graph well. We'll see what happens here. It might be in his standard window. That's always a good place to start, so I will do that. So let me hit it, zoom standard, which is option 6 under the zoom feature right here. And it looks like not only is it graphing the way we expected, right, where it crossed at these two zeros and bounced off of this zero, but look, it also happened to fit in this window. If it didn't, I'd have to go in window and adjust it a little bit. But a lot of times these polynomial functions will have minimums or maximums that are beyond the standard window, and then you have to go ahead and raise it and lower it accordingly. Okay, so now what I'm going to do is I'm going to come up with the minimum and maximum using my calculate feature of this calculator. Right? I want this minimum and maximum, and we'll be plotting those points as well. So let's go ahead and do that. So we'll hit second, calculate, and let's find the minimum value. So we'll go down here. We have to left and right arrow till we get to the left and right of what we're calculating. So it asks for a left bound, and we'll go ahead and hit enter. And now it asks for a right bound, and we'll go over here, hit enter, and we'll bring it just inside that set of boundaries. And here are the coordinates to the minimum point. It looks like it's negative 1 point, and I'll just round off to 5.7, and negative 3.12. So there's my minimum, right? I'm going to go ahead over here and plot that. So over here I would have negative 1.57 would bring me about a little more than halfway here, and then down at negative 123.12 would be somewhere about here. Okay, and I'm going to go ahead and actually plot those coordinates because it'll be easier when I go to figure out where the areas of domain and range and increasing and decreasing are. I could go ahead and see that a little better with having those coordinates right there. So let me do that. Let me put this in here as this is the point negative 1.57 and negative 3.12. Okay. All right, let me do the maximum, which is a very similar kind of calculation. I'm going to go ahead and go back to second, calculate. I'm going to go down to maximum this time. And this time I need a left boundary, which is now the cursor. I use my right and left arrow, and it's to the left of this maximum point. I hit enter. Now I have to go up over that maximum so that I give it a right boundary so the calculator knows in what area is it trying to find this point. And so now I hit the guess point by just backing up some in between those boundaries, and I hit enter, and it tells me that the maximum point is right here. It says it is 0.32, I would say, rounded off to the second place, and 8.64 rounded off to the second place. And then I'm going to go ahead and plot that on my graph. So I have here 0.32, a third of the way approximately over to 1, and then up at 8.64. And this is just a little bit higher than the y-intercept, right? Okay, so that's going to be enough for me to have the guide to be able to go ahead and graph this. And let me plot this. Let me put the coordinates on this point. That's going to be what? 0.32, and 8.64. Okay, now I'm going to go ahead and just kind of connect the dots. We know that the function was going up on the right. It's coming down to this minimum point. It's crossing back through my 0 of -1. It's coming up and it's crossing not only through my y-intercept, but it reaches up to that maximum point that we calculated, and then it comes down, and it's going to go ahead and bounce off of here because that had a multiplicity of 2 as a 0. And I'm getting a graph something like that, and you can see my calculator. Of course, it's not a perfect drawing or replica of it, but it should have some similarity, and it does. Now, the only thing left is to do these intervals, right? Okay, so we know domain values are all the possible x values, and it turns out on polynomial functions that it always is from, eventually this thing is slightly slanted out to the left. Eventually, I'll find points way out and up that would cover -infinity in the x direction. And so all the possible inputs of this are from -infinity and out to eventually +infinity, are all values that could be put in this function. But notice on this even degree function, this 4th degree function, there was a limitation in the y values. With odd degree functions like, a graph like this, they'll go from -infinity to +infinity or vice versa. But in this particular case, there was a limitation, and it's one of the reasons I plotted the coordinates of the point, because the lowest y value that this function's ever going to reach is the y coordinate to this, which was -3.12. So that's going to be the limit, the lower limit of my range will be negative. Remember, ranges are y values. And then the maximum, this thing will eventually reach up to +infinity because these arrows are indicating this is going to continue on, right? Okay, now, the intervals of increase and decrease, we've talked about this a couple of times. These are really the domain broken up into the sections of the graph that are increasing and the sections of the graph that are decreasing. So this should still count up eventually from -infinity to +infinity, which is our domain. So let's look at the sections where this graph is increasing. It looks like there are actually two places. One would be here, from here to here, and then the other one is from here to here. So the x-coordinate that the increase begins on in this segment is -1.57. So I'm going to say that this function is increasing from -1.57 until it reaches this point right here, right? This maximum point. And that x-coordinate is 0.32. And you can watch over here also. I have these values right here. You don't have to pick them just off the graph. It might be hard to see. But so I went from -1.57 here to 0.32 up here, right? And so that's going to be the first interval over which this function is increasing. Okay, and the other one goes from this 0 of 2 eventually out to infinity. This is an increasing function over that interval. And so that will also be another one, and this is going to be here at from 2 to infinity. Okay, now we have to fill in the decreasing segments of it that are in between these two. Well, the decreasing one, that started here at, it's going to start at -infinity, and it's going to go to this -1.57 point, and that is going to be this right here. Then I'm going to write from -infinity to -1.57, and the other decrease is from the maximum point, right, down to 2. So I'm going to say that the x values over which the function is decreasing in this segment would be from 0.32 to 2. From 0.32 to 2. And I use brackets on all the endpoints where infinity was not included because it's including those points, right? By the way, you could just track the overall domain here because you went from -infinity to negative 1.57, that was this decrease right here. And then you went from negative 1.57 to 0.32, that was this increase right there, right, this increase. And then you went from 0.32 to 2, and that was this decrease right here. And then you went from 2 to infinity, and that was this final increase right here. And I think we're done.